Rotation. In this video, we're going to learn 2D and 3D rotation matrices as linear transformations. And we're going to see right-hand rule to rotate about an axis. The outcomes are understanding the relationship between rotation matrices and coordinate frames and a common 2D and 3D rotation convention. Rotation is a circular movement of an object around the center. A three-dimensional object can always be rotated about an infinite number of imaginary lines. We call these lines rotation axes. First, we're going to derive the 2D rotation matrix. Here we have our 2D Cartesian space. We have two unit vectors, E1 and E2. And any point in this plane, for example this point, we call it X, with coordinates 0.4 and 0.5. Any point in this coordinate can be defined as a linear combination of E1 and E2. For this reason, we call E1 and E2 the basis vectors. If we rotate E1 and E2 using an arbitrary angle theta, they remain perpendicular. The result will be two new vectors, E1 prime and E2 prime. Of course, we can also use E1 prime and E2 prime to identify any point in the plane. Now the question is, what is the linear map that transforms E1 and E2 to E1 prime and E2 prime, and what's the matrix representation for it? First, using some basic trigonometry, we recognize that E1 prime and E2 prime can be written as following vectors in the blue coordinates. Let's see why. We have E1 and E2. This was E1 prime. If this angle is theta, this will be cosine of theta. And this will be sine of theta. Therefore, E1 prime in E1 and E2 basis takes this form. And we learned that we can write it as this vector. A remark: this way of finding the solution by using a linear combinations of different dimensions or bases is a fundamental property of linear maps and is called superposition. Now let's find the relationship between a vector v defined in the red coordinate frame, E1 prime and E2 prime, and another arbitrary vector v prime that is defined in the blue coordinate frame. Now we would like these two vectors to be equal. So we set them to be equal. Notice that they use different bases. Now let's write this in the matrix form. We write our vector b prime and substitute the relationship we derived according to v and the rotation angle theta into our vector. Now we can recognize that this vector is a result of multiplying this matrix here and a vector b. We call this matrix R. So we just proved that v prime is the result of applying a rotation matrix to v. The question is, how do we know what's the positive direction of rotation? The convention is using the right-hand rule. If you keep your thumb along any axis that you would like to rotate an object, and if you move your wrist inward, then that's the positive direction for rotation. In this example, if you keep your thumb along the z-axis, you see the red vector shows the positive rotation direction. A common convention in engineering and physics is calling the rotation about a vector that is along the vehicle rho, a rotation about direction that points to the side is called pitch, and the rotation about the vertical axis that defines the heading of the vehicle is called yaw angle. Now we're going to prove 3D rotation matrices. The first question is, if you have a rotation about z-axis, prove that we will get the following matrix as our rotation matrix. Now the answer is very similar to the previous case, except it's a little more complicated because we have 3 bases. Similarly, we define our E1, E2, and 3 bases. Notice that E1 is along the x-axis, E2 is along the y-axis, and E3 is along the z-axis. If we have a gamma rotation, gamma is the angle, about the z-axis, we will get 3 new unit vectors. Again, using basic trigonometry, we learned that E1, E2, and E3 takes the following form. Notice that E3 and E3 prime are the same because E3 is the axis of rotation. Now let's prove it using the same method. We define a vector v using the rotated basis, and we define another vector v prime using the original basis, and we set them to be equal. This way we will find a relationship for each entry of v prime based on v and the rotation angle. If we do that and convert it to the matrix form, we learn that a rotation matrix is indeed what the question was asking. Now here are two more matrices for you to practice. Try to derive rotation about y and x axis. Next time, we're going to talk about affine transformation.